That's a really fun commercial that May in Space and our partner at Lowe's put together when we were launching this printer, which is now on the space station, and now we are doing this work. Let's talk about why we're doing it. Here we are. That's us somewhere out in the middle of the universe. Silicon Valley is an interesting place. This is where our company is located for a really good reason. Well, first of all, we actually came out of Singularity University, but more so it's because this is, like Salim was talking about earlier, the land of moonshot thinking. And what we do is quite literally a moonshot. And we're really focused on how do we get people living off of planet Earth, and what are the ways to make our species exist in more than just one place. One driving question that after we've been doing this for so long, the thing that's driving me and the question I've been trying to answer pretty fundamentally is a planetary surface really the best place for all of our advancing industrial needs? As we see the Moore's law allow us to have better and better technology, the back end of that is the industrial process that gets us at. Is it best to do that on a planetary surface or not? That question has actually driven a lot of the work we're doing in the company to try to understand that. And so keep that question in your mind while I tell you about what we do. So obviously space, we've done a lot of amazing things in space. We've built cars that drive on other worlds, right? Just these amazing feats. Most people, and maybe some of you even, but I know when I go around the world and talk about this, most people think that if we've been doing this since the 60s, well, we must have hundreds of people living in space by now. We must have the city on the moon by now. But the reality is that today only 555 people have ever left planet Earth. So it's really still a very small amount of people that have left the planet. So the question is why? Like why, if we've been doing this for half a century, why have we had such a small number leave? And part of the answer is because this is how we explore space today. We're much like the goldfish. We have to bottle up a little bit of Earth and bring it with us everywhere we go. So when we're building 3D printers for the space station, we're thinking a lot about what life is like on board a spaceship. And the fact that in reality, the spaceship, the space station, is a mini Earth. It has all the things that Earth gives us for free that we don't even think twice about. The fact that you have to create a breathable, livable atmosphere and have all the food you need and recycle the water. And the spaceship above Earth is really a mini version of Earth. Earth is a spaceship as well. So when we think about how do we all get to go to space one day, which is one of my biggest inspirations, I also have to remember that we already are there. We're all in a spaceship today. Only 555 of us have ever left the spaceship, right? So when we design things for space, we're also thinking about how that helps us on Earth. So I'll tell you a story about the printer that's on the space station, which one of my favorite stories. This is Butch Wilmore. He was the commander of the space station when we launched the printer. And commander of the space station is kind of like the Captain Kirk of the ISS. And so he's in charge. And one day he mentions over the headset, that we're in our control room controlling the printer, and he mentions over the loop that he had lost his ratchet tool, his wrench. And at first we were thinking, how does an astronaut lose a tool like that? That seems like a pretty important thing not to lose. But when you think about it, well, first of all, everything floats. So maybe Butch was working on something and you don't set down your tool, you just kind of like let go of it and move on to something else and it stays floating there. But there's air currents and ventilation, so maybe the wrench this is why I have this picture up here. Maybe look how cluttered the space station is. It could have floated inside a spacesuit or behind the tangle of wires at the bottom of the image. So the space station today is not that clean-walled 2001 Space Odyssey space station that we all probably imagine space is like. It's actually a cluttered environment. And the reason why is because we have to bring up so much extra things into space in case something fails. There's redundancy across the board for everything. So Butch says he's missing his tool, and we go back to NASA and we say, hey, you know what, let's this perfect opportunity. Let's design that tool and have it 3D printed for Butch. So this is the story of how we did that. This is the printer that was there. We have two there now. The one you saw in the Lowe's video is the second one. But at the time of the story, we had our first printer there. Really an experimental device that we were doing with NASA. So we started in CAD. We designed this tool. NASA gave us requirements. It had to be printed in one part, no assembly required. Butch should take it out of the printer. It has ratcheting mechanisms inside. The interesting thing, this tool doesn't really fit the case, but we'll come back to it soon, is that the things that we print in space only have to exist in software and in space. They never really have to exist in this environment of one gravity, right? So that's really important for why we're doing what we're doing. So here's the tool. We printed it. We go through a big NASA safety process. The first time NASA would ever, we printed this out in our lab. We shipped it to NASA, and they held it, and the safety panel held it. And that's the first time they would ever hold a thing and decide if it could go to space or not. And that wasn't really the thing. We said, trust us, the printer in space will build the thing that you're holding. And so they passed, it went through the safety, it passed. And then 5 days later, so from the moment Butch said he needed the tool, 5 days later, we're ready to go. And this is our command center at Made in Space, very simple little mission control. And we're connecting to the space station via the payload operations center at NASA. So we take our design file, we ship it through some software protocols to NASA, where then they uplink it to the space station. This happens in a matter of minutes when the space station's over a good commanding window. NASA installs it onto a laptop computer that's on the space station, and then inside this big glove box is the printer that you saw earlier. So at this moment, NASA says you're free to go. You can command the printer. So we kind of remote desktop into the 3D printer. That's how we control it. And we send the file over to the printer and hit print. It takes about 2 hours for this part to be printed. But what's more interesting is that to astronauts like Butch, the printer is like a magic box. They're off doing all these other activities. They have to keep the space station in space. So to them, it's this magic box that every time they open the door, something's inside. They take it out. They close the door. They go do something else. And then they come back, and when they open up, there's something else inside. And so imagine, being in space must be cool. You get to look out the window and see Earth, but when you're spending your whole day, 8 hours a day, just maintaining the space station, little things like what's in the magic box today becomes a really exciting part of life. So we were experiencing this magic box fun, and in this case, Butch left an empty box and said, I really wish I had that tool. 5 days later, he comes back to open the box again. And this is 2 hours after we had printed the tool. And here's Butch opening the door, has no idea what's inside his box today. And then my favorite picture of them all, the money shot, Butch holding his tool. And so the amazing thing about this picture is it was taken 2 hours after we sent the digital file to space. 2 hours. That's the fastest hardware has ever been sent to an astronaut in space. And if Butch were on Mars, I would be telling you the same exact story, because we're sending things through radio communications. The difference in distance is minimal. So, and if it were, one day it will be a metal 3D printer, or will be a printer building a house on the moon out of the moon dirt. And it's always going to be a very similar story. We design things on Earth, and we send the digital information to the robot that builds it where we need it. So now we have our new printer on the space station, the one that you saw in the commercial earlier. This is actually a commercial facility, which means Made in Space owns it. We have a little bit of real estate on the space station, and we sell a service of manufacturing in space. Just like SpaceX sells a service of launching your satellite into space, we can 3D print it for you there. And so now we're actually every day operating this printer, not just for NASA, but for commercial users around the world, designing satellites that they can manufacture, new types of experiments for the space station. We're going to have to do a better applause than that. All right. So this is one of the really fun parts about what we've been doing lately. So I'm going to jump into why this is important. Why is it important that we can manufacture off planet Earth at all, right? Well, to explain that, I'll go back to the beginning. This is Yuri Gagarin. He's the first person ever to leave planet Earth, April 12th, 1961. And he launches out the Baikonur Cosmodrome on the pinnacle of technological achievement at the time. It's the Vostok rocket, launches Yuri into space. Now we fast forward a half a century later, and we look at how astronauts go to space today. Here's Butch. We already talked about Butch, so it's easy to tell the story, but it's really any astronaut going to the space station. It's the same exact story. Today, how do they get to the space station? Well, on none other than the Soyuz rocket. And to me, they look identical, and the reason why is because they almost are. The Soyuz went into operation only 6 years after Yuri's first flight. The technology is very similar, launching from the same location on Earth even. So the point is that we're using the same exact technology to put things into space that we always have been. And even if you're looking at a different launch vehicle, whether it's Apollo or the space shuttle, things that look totally different than a Soyuz or Vostok, it's still the same basic technology. It's chemical propulsion. Only about 2% of a rocket is the thing that we want in space, and the other 98% is the fuel and the structure and the rocket engines and all the things to get it there. The reason why is it takes actually a tremendous amount of energy to escape what we call Earth's gravity well. We sit at the bottom of this pit of gravity, and it takes this tremendous amount of energy to get out of it. So for the history of spaceflight, we've always been launching out of the gravity well and requiring this huge amount of energy to get there. The astronauts inside the capsule in this picture, traveling to the moon, were going about the speed of 10 times a rifle bullet when they escaped Earth's gravitational pull and got on their way to the moon. So, and anything we've ever sent beyond Earth's gravitational pull has had to go that fast, 10 times the speed of a rifle bullet. So it's like this amazing amount of energy. And the way we look at it at Made in Space is that it's a supply chain problem. This is not how it's typically looked at, but in the industry of 3D printing, we recognize that quite often, that 3D printing has the ability to disrupt supply chains, and space obviously has a supply chain problem. We've been transporting to and from space exactly the same way for over 55 years, and there is obviously room for disruption. How does that supply chain look today? Well, we have to design our rockets to fit on barges so they can be shipped across oceans. Some rockets even are put on the back of trains to be brought to the launch pad. So if you think about it this way, since everything in space has to fit into a rocket, into the diameter of a rocket, and now the size of a rocket has to fit onto a railroad track, that means the size of the things we have in space are dictated by the width of a railroad track. Like that is a completely unnecessary constraint, but that is how space has always been done. To put it into kind of like a money perspective, a liter of water in low Earth orbit costs about $10,000. That's $10,000 a kilogram to launch today. So it's just insanely expensive. So while we've seen this in the news a lot lately, reusable rockets that land back at the launch pad, which is really, really important. We need to drive the cost of launch down. But while everybody was working to make the better rocket, we just asked a fundamentally different question. What if you didn't have to launch anything at all, right? What if in the future everything in space were made in space? And that's kind of the name of the company. And I think that's really important. Asking fundamentally different questions usually leads to fundamentally different results. And that's where the idea of the company came from, is what if we didn't have to launch anything at all? What would that look like? And part of that vision for us is that, well, first of all, you don't have to worry about launch, right? So that means nothing has to survive the loads of launch, the high G loads. And more than that, nothing has to fit inside of a rocket anymore. So you could build antenna dishes that are a kilometer across and could provide broadband internet directly to a cell phone anywhere on Earth, if you could build very big antennas. You could build all kinds of things that way, and all you have to do is launch these smaller robotic devices, robots in space that can build those things. So this really became a driving motivator for us at Made in Space. And but what really matters is what we're building and not how we build it. The robot or the 3D printer that's the magic box. That's not really what's important. What's important is the things that we can build, right? So a really good parallel to that is the story of New Horizons. This is the spacecraft that last year made its way to Pluto. And I'm sure most of you saw this in the news. It was this amazing kind of moment where we finally got close enough to Pluto to actually look at it, to take images of it. The image taken by the New Horizons team of Pluto was voted by Wikipedia the best picture of the year. It was the most important picture taken last year. And part of the story that most people don't know is that it took 10 years for the New Horizons spacecraft to launch and get all the way to Pluto to get this picture. And when it launched, the software to do all the compression and to capture this amazing picture, that software wasn't developed. They launched the spacecraft knowing that they had 10 more years and they could anticipate the progress of technology, build better software, build better algorithms, and then uplink the software to the spacecraft before it had to take this image. So, it's this amazing story that we can send these spacecraft into space and not really need them to do anything for years, maybe even a decade. And we can send the software or the update to them. So in much the same way that's how New Horizons got this image, that's what we're doing with hardware. We send this. The idea is we can send these spacecraft into space, and then when we need something, send the information to the spacecraft and tell it what to build. So what matters is what we build, not really how we build it. And to kind of drive that point home, and this to me is probably one of the most important things that we work on, but also where the future's really headed for manufacturing. So this is a story about the women of Apollo. Most people don't know the women of Apollo. We know about the white men who got to walk on the moon. But this story is actually maybe even more important because we wouldn't have landed on the moon without them. These women were at JPL, and they were actually doing all the math to get people to the moon and back home safely. At the time, the profession that these women had, and it wasn't just women doing it, the profession was called computer. These people were computers. That was their job title. And it almost sounds silly, to me, I wasn't alive when people were computers, but there was a point in time that happened, that entire giant rooms were filled with people doing computation because computers weren't advanced enough or affordable enough to do that. So we obviously know where things have headed since then. We don't have people as computers. We've built computers, and people become the mentors to those computers. They ask the computer for results, and they get those results. Now, today, when we build spacecraft, it's still a very hands-on exercise. Every spacecraft that's ever been designed has been designed by a room full of engineers in a cubicle farm, right? Just like that room of human computers. And everything they create is created by, first of all, the ability of the human brain to conceive of it, and then the ability for one hand on a keyboard and one hand on a mouse to manipulate some CAD on a computer to create whatever it is they're imagining, right? So extremely limited to what we can actually produce, and that's how all spacecraft have ever been designed, and not just spacecraft, obviously, mostly everything in our physical world. We're getting really close to the point, and it's already happening in some areas where the computer and the software is doing the design for us. We call it genetic algorithms or generative design. And here's a really good example of what that looks like. But what you do is you basically feed the software just the constraints of the environment. You say, I need a 100-meter antenna. It's going to be in low Earth orbit. It's going to see these types of loads every time we have to boost its altitude, and it has this solar radiation pressure. You don't tell the software, here's what it looks like, optimize it. You just say, I have that environment, give me the best answer. And then the software, using cloud computing, goes through thousands of different iterations. It evolves the best design based on the environment you gave it. And then maybe you start in the morning, and by the time you go out to lunch, you have the computer is giving you. It said, I came up with 10,000 ideas. Here's the optimal best 3. And oh, by the way, these can only be 3D printed. They're too complex to be made by hand. So now you have something that can't be imagined by the human brain, can't be created with the dexterity of the human hand, and can only be created if it were created in 0 gravity by 3D printers. And I think that's where we're headed just with design and engineering in general. It's, give it another generation from now, and I think it will be just as funny to hear that engineers used to be people as it is today to hear that computers used to be people. That doesn't mean that engineers go away as a profession. I'm an engineer. I hope that doesn't happen. What it means is that the power of the engineer gets far, far better. What used to take in the future, what used to be a room of engineers to solve that problem of design of a satellite means that maybe in the future just one engineer and the mentorship to the machines can get the same result. So one engineer in this crowd could have their own engineering company that used to take hundreds of people. And I think that is a really, really powerful thing that is right on the horizon. So moving along, how are we doing that? We have a new program called Archinaut. This is with NASA, and then we have Northrop Grumman and Oceaneering as partners on this program. We're building a spacecraft. We call it Archinaut, like architecture astronaut. And when it gets into space, it actually builds those really big things. So we take manufacturing, additive manufacturing, robotics, and assembly, and we start to build very big things in space. So this is a big program we're working on today to try to bring that type of future to life. What does it look like? Well, if today's satellite looks like something that can pack up into a rocket and kind of pop out some solar panels, we imagine that when you remove those constraints, you'll have spacecraft that look completely different. You'll have giant, big platforms in space that can do all sorts of interesting things. What matters most, though, is that this isn't really just about manufacturing. What's really important is that we're talking about new types of processing. When we build something in 0 gravity that only can exist there, we're taking advantage of the fact that we're in a 0 gravity environment and we're manufacturing differently. The process that we manufacture this very large antenna in space probably doesn't even work on Earth. It's a process specifically for space. And this is really important because historically new processes have always unlocked new industries. And I'll share two really good examples there. The first is 17th century England. The hardwood birch forests were being cut down because England was burning that hardwood for energy. The forests were being completely decimated. It was the only way to get the energy, and England knew that they were running out of their energy source. They also knew that in these water-filled mines was coal, and if there was a way to get the water out of the mines, they could have the coal, and they could burn the coal for energy. But there wasn't a sufficient technology to get the water out of the mines. And then bright gentleman named Abraham Darby came along and invented a new process, and the process is the coke oven. The coke oven allowed for the high enough temperatures to be created to create steel, and the steel was used to do many things, one of which was to build pumps, and the pumps extracted the water from the mines, and now the coal was unleashed, and now England had coal for energy. The coal could be fed into the coke oven to make more steel, or be burned for energy. So this one little process, the process of creating the coke oven to get these really high temperatures, unlocked what we now call the first industrial revolution or the machine age. Without that one new process that Darby created, we wouldn't have had the industrial revolution. And without that, everything we know today wouldn't have existed because we built all of our technology on top of that one piece of foundation. So new processes unlock new industries. Another great one is this. What do these 3 pictures share in common? Anybody? Just yell it out. Aluminum, right? Yeah, so, and I guess this is the right crowd. Everybody probably already knows the story, but why is aluminum so cheap that we can throw it away, so pure that we can make space vehicles out of it or make these beautiful devices? It's because a new process unlocked aluminum. It used to not be that readily available. Aluminum was really the most expensive metal on Earth. But it is totally abundant. And the story is that Charles Hall, this is invented by a few people at the same time, but this story is about Charles. He's 23 years old. He's in college class in Ohio when his professor says the first person to figure out how to make cheap aluminum will be rich. And he goes home, talks to his chemist sister. The two of them come up with an electrolysis process to unlock aluminum from fluoride salts. The rest is history. Aluminum becomes very, very abundant and cheap because of this new type of electrolysis process. So once again, this new process unlocked a new industry that we all rely on today. Well, I'm sure everybody here will touch something made of aluminum today. So the big question that I ask to my team is, what new processes might be created in space if we can leverage the unique aspects of the space environment, whether it's the fact that you have zero gravity, or if you spin something in a centrifuge, you can have any gravity you want for manufacturing. That's interesting. You have a vacuum. A lot of manufacturing techniques already require a vacuum today, and in space it's free. And you can control the vacuum. And there's just a whole bunch of other really interesting aspects of the space environment that allow us to do something entirely new. One of the things that we're doing about that today is, and we actually have a booth here that we have this at the booth, we're making optical fiber in space. This is really interesting because it turns out, just from pure physics, that there's a class of optical fiber that if you could turn the gravity part of the equation to zero, the fiber becomes 100 times better than silica fiber in terms of attenuation. So that means that if you can make this in zero gravity, you'll have the best fiber that's physically possible to be made. So think about how making that in space transforms industries on Earth, industries that rely on optical fiber for communications or medical applications or lasers. So we're working on that today to help show that space really is a useful place where you can make products and bring them back to Earth. And I think that's really important because when I go back to the thought of life on board a spaceship, and I think about, we started our company trying to solve the problems of life on spaceships and life when people are on the moon or on Mars. But the more we work on it, the more we realize that we live on a spaceship. And these technologies aren't just technologies that are good for space and then can get spun off for Earth. But actually, what we're doing helps enable us to make Earth a better place. I do believe that we will go live on Mars one day. I'm in that boat that's important for humanity. But I also believe that we've got it really good here. This planet already wants to keep us alive. You can live longer here than you can on any other world, and it's because this is where we came from. And we need to remember that. We need to remember that this is a place worth protecting. And a lot of people in my groups like to talk about moving to another planet. Let's go live on Mars. Let's change worlds. I think what's more important is to talk about changing the world. And space actually very, very, very literally does that. And it's because there is a dark side of industrialization. We have to burn fossil fuels or create energy, and no matter how you do it, there's always wasted heat. That's the second law of thermodynamics. So we have our atmosphere as a heat sink, or our oceans as a heat sink to dump that waste heat into, and there's no getting around it. Like, that changes our environment. We are living in a closed system spaceship, and when we put heat into the system, it has to go somewhere, and we're starting to see that. We turn mountains into holes in the ground to get our resources, and there's no reason that we have to do that. One day we'll run out of mountains to turn into holes in the ground, and it will actually be cheaper to go to space to get the resources. There's companies working on doing just that. So space becomes the place that we just naturally should go to do our industrialization. So when I come back to that question that I asked earlier, is a planetary surface really the best place for our advancing industrial needs? I think today maybe it just happens to work well for us, but inevitably the answer is no. We will bring industry to space because it will economically be better for us, but in terms of actually protecting the spaceship, it'll be the only thing that can do it. So I'll leave you all with that and say, let's go space. Thanks.